Again, I'm Demani.
My name is Alejandro Jimenez.
And I'm Emmanuel Ayala.
Our mentor is Kabe Ahadi. He is a member of the summer research group here at UCSB in the MRL, Material Research Laboratory. Our group presentation on oxide thin film technology and its use in current electronics applications. Thinking big picture, we've hit a red brick wall. To explain that further, the International Technology Roadmap for Semiconductors, or the ITRS, projects that within a few years, semiconductor technology will no longer advance as it was in prior years. Looking closely at Moore's Law, it says that transistor density is supposed to double every 2 years. What we see happening is that no longer are we able to manipulate the materials that are being used in electronics to give us outcomes like faster processing speed, smaller, less expensive, all things that we desire in electronics. This trend has been true for the last 45 years, and with the way things are headed, it's looking that it will no longer be true. And so one of the ways we hope to overcome this red brick wall is by coming at it from a different angle, coming at this whole idea from a perspective of changing one of the variables. In this case, we're changing the material. What we've been using so far has been silicon. It's one of the most popular materials used in electronics, and what we're pushing for is, like we said, using oxides. Oxide thin film semiconductors are found in a collection of electronics applications. Some popular ones, power electronics. If you see this picture right here, this is an integrated circuit consisting of many different things, but more importantly, you can see transistors. Transistors are crucial for computing, for processing. We know that zinc oxide is a material that's being used in transistors currently. So you see oxides in electronics at the present. Solar cells is another important application. If you look right here, this is a picture of the International Space Station. You can imagine that the materials that go into something like a space station would be very important, and to see that we have oxides in space is just a testament to how reliable and truly advanced oxides can be. Another picture right here, if anyone here has a Samsung cell phone, or maybe a Samsung computer or television, Samsung is popular for a material known as indium gallium zinc oxide, IGZO. They use it in their thin film transistors that then are used in displays. This is a picture of a TV screen. Like I said, if you have a Samsung device, there's a possibility that you're actually already using IGZO, which is an oxide.
So one of the benefits that we see from oxides can be viewed when we look at the material composition of the Earth's outer crust. We know that the Earth's outer crust is composed of 99% oxides. Now this tells us that the oxides are naturally stable and they are a perfect candidate for the use of power electronics. Some of its mechanical properties, robustness, this is a very specific characterization because in the use of high-end power electronics, we want our material to be strong and last a long time. It has also tunable properties that we are hoping to explore furthermore in the hopes of creating a better semiconductor material. And of course, oxides, they withstand higher currents and higher temperatures. Now, the way we grow our thin films, we do that by using an MBE.
This right here is a picture of an MBE, otherwise molecular beam epitaxy. This picture is taken from with the MBE lab here at UCSB, which is one of the best MBE labs in the world in academics as far as growing thin films and that sort of thing. This is a diagram of what an MBE does. MBE is important for this type of research because we need clean and pure ways of growing thin films without any sort of contamination. How this achieves that is within this chamber and actually the whole system, 13 orders of magnitude lower than standard ambient pressure. So ambient pressure is what we're feeling right now. 13 orders of magnitude lower exists within this chamber, meaning it's one of the lowest pressures on this Earth that's even achievable. And from within this system, we can then ensure that there is no sort of contamination that's going to enter our thin film as we grow them. Growing is a term that we use for deposition, or laying the atoms on top of our substrate. So we see right here, this is the entry chamber. We load our substrate, which is a flat surface, usually given so that we can grow materials on them. It enters here, and once this system, once this chamber has the same pressure as the rest of the system, we can then move our substrate into the buffer chamber. From here, we can then put it into the main chamber. And as you see, we heat our wafer to whatever temperature it is before we deposit. Each one of these diffusion cells holds possibly a different type of material that can then be vaporized and shot right on top of our substrate. And that is how we grow it. One of the important, once we are done, Once we're done, we can then remove it from this chamber and move on to the next step of our experiment, which is then characterizing its optical properties.
The way we do that is by ellipsometry and polarized light. The way it works, you have a light source and a polarizer. You have a polarized light shining into the sample. And of course, you get a reflection out of it. The analyzer and the detector catches those changes, and the phase shift and the intensity will change. And just from getting our phase shift, we can have our property like its roughness, its thickness, and optical properties, such as the index of refraction of our thin film. Now, this ellipsometry data corresponds to our STO film, which stands for film titanate. It tells us two things. As the photon energy increases, the black line represents the index of refraction, the changes, and the blue line represents the light that's being absorbed. Now, the ellipsometry data is very important because it gives us information about it. It can tell us anything that's wrong with our thin film, but in this case, our STO film looks perfectly fine. That's the way it should look like. After we have found our ellipsometry data, it's important that we look for electrical components or electrical data as well.
Okay, so the first part of this, or first process of getting the electric conductivity of the thin film is to first get 4 contacts placed on the thin film. So we use titanium and gold. How we do this is we go to the electron beam evaporation, which is located in the nanofab. We vaporize the titanium and gold, which is located in this crucible with this electron beam gun. And
it's important to have these contacts established for when we take our Hall measurements. Hall measurements are, it's almost a surface voltage that when you have a magnetic flux applied to our material and a current at the same time, it produces a voltage perpendicular to both of these two. If you think of the right-hand rule, it's a vector that's perpendicular to 2 perpendicular vectors. It produces this Hall voltage, which is important for measuring things like carrier mobility, carrier concentration, and carrier type. A carrier is a positive or negative charge that moves through a material. Our measurement results specifically our oxide, which was STO, or strontium titanate, was here. You see the sheet charge density is 9.39 times 10 to the 14 per centimeter squared. We know that that number is very good. We were actually pleased to see that number. Our mobility is 5.2. STO, this test was done at room temperature, but STO done, this same test done on STO at 2, 3, 4 Kelvin produced a mobility of around 30,000. And that is far exceeding any sort of current technology used. And what we're hoping to do is take that same mobility found at that low temperature and bring it up to room temperature where we are using our electronics. If you look here, this is a quick picture of the Hall measurement tool that we use. This one's in the MB as well. This is the magnet I was talking about. This magnet's going to produce the flux through this tiny little substrate right here. You also have a picture right here of our substrate with each 4 gold contact on there. And, yep.
So when we finish characterizing our material, we want to know what's the current voltage it can hold before it starts leaking. And how we do that is we go to the probe station and we put 1 probe on the drain, 1 probe on the source, and 1 probe on the gate. This shows how much we have on the gate, how much voltage we have. This shows how much voltage we're applying to the drain and source, and this is being swept through from 0 to 6. And what we're actually measuring is how much the current is in the channel. So this shows the current that's in the channel at the moment. So we apply it at 0.1 intervals to the gate right here, as you can see. Each one of these lines mean 0.1 more each line. So what we want to see is now we're able to turn on and off this transistor. As you can see, when we're starting off, it's at 0, so that means pretty much the current is at 0. It means that the transistor is a really good transistor, and this is what we're looking for when we want to add it to our technology, because we want to be able to turn it on and off easily.
All right, and in conclusion, again, these are our measurement results. The sheet charge density was probably the more promising number of the two. We see here that our oxide had unique optical properties that can then be applied to any application, and also that it has and behaves like a transistor. All things important in considering its material application in electronics. We wanted to say thank you, first of all, to CISA and to UCSB. This has been an amazing opportunity. Anshul, our super mentor. Ellie, who's not here, but has been an amazing help. And then also Jens, thank you for all of your input through the stages of this. And of course, Kave, our mentor. Thank you.